All right, let's talk about the bacteria population. All right, so here is the property of the bacteria population. The time rate of change of a bacteria population is proportional to the population itself. Right, so it kind of makes sense, right? Because if you have the bigger population, then the population grows faster. For example, if you have, say, only 10 bacteria to begin with, say it doubles every minute or something like that, then in 1 minute, 10 becomes 20 bacteria, which is a 10 bacteria increase in a minute. But if you have 1,000,000 bacteria to begin with, and if it doubles in a minute, it becomes 2,000,000, which means that it's a 1,000,000 bacteria increase in a minute. So you can see that the bigger the population is, the faster the population grows. So it makes sense, right? All right, so let's try to rewrite this description in math notation. All right, so first thing is the time rate of change of a bacteria population. Let's say bacterial population, we're gonna use the letter P. All right, so here. So bacteria population, I'm going to use letter P. So since it depends on time, so I'm going to use a P of T. Right? And time rate of change is the derivative, right? So this is the derivative. So this is the derivative with respect to time. Right? And it says proportional to. So this is another way of saying is a constant multiple of, right? And the population is P, right? So let's try to come up with a differential equation describing exactly the same thing, right? So differential equation. So time derivative, a rate of change of bacterial population, which is easy to describe in math notation, right? It's going to be derivative of the population P with respect to time. So dP over dt, right? It's proportional to, so this is going to be is equal to constant multiple. I'm going to use K as a constant multiple of the population itself, so which is P. All right. So this is the differential equation describing exactly the same thing. Right? And also there's something called the initial value condition. Since the initial population is given to be P0, so we know that when the population, when T is equal to 0, is going to be P sub 0. Right? So this is the differential equation and the initial value condition. Right? And let's look a little bit more closely at the differential equation. All right, so we're talking about a function whose derivative is almost the original function. And we actually know such a function, right? This is one of those favorite functions that the derivative is very simple to find. So which is the exponential function. Right, so we can make an educational guess what the solution is. Right, so what would be the solution? Right, and the solution came out to be exponential function. So it's going to be P of T is going to be equal to the initial population P0 times exponential function e to the kt. Right? At this point, we don't know how to find that, but we can at least verify this actually follows the differential equation. Right? So let's do that. So given that, let's try to find the derivative. So it's going to be dp over dt. Right? So this is going to be equal to, P0 is a constant, so just the initial population stays there. All right, derivative of e to the kt would be e to the kt, then by chain rule, multiply by derivative of kt would be k. All right, so you can see that here, P0 e to the kt is exactly the same as P of t. So we have k times P of t, so k times P of t, which is kp, which follows this differential equation. All right, so the definition, the solution of this differential equation is P of t is equal to P0, initial population, times e to the kt. All right, so solution is exponential function. All right, that's the bacteria population model. All right, that's it. I hope that this was clear.